Okay, welcome back, everybody. I hope that you all had a good weekend. Good holiday? Yes. Is this that one? Okay, thank you. Yes. Yes. Okay, if you did not get your exam last time, make sure you get that from me before you leave today. We are two separate pieces. Okay, your name's on it? Okay, it's fine. Thank you. Make sure you click in. We're in 2.1, right? You had the pleasure of doing that take-home assignment, and you got to see some of the algebra that can get in the way of the ideas, right? The concepts are there, right? The difference quotient, f of x minus f of a over x minus a, take the limit as x goes to a, right? That's the idea. But the algebra behind it can be a little bit tough. We're going to do more today. I know that you're excited about that. So here's where we were, right? The whole idea was we picked a point, we called the x-coordinate a, the y-coordinate was in f of a. The other x-coordinate, well, we called it x, and then the y-coordinate was f of x, and then we just dragged that point over here. To do that, we had to apply what? The limit as what approached what for this to happen? X approached a of that difference quotient. But there's a second approach, same exact geometric idea, but instead of using the point a f of a and x f of x, we use something else. We still use a f of a, yay, nothing's changed there. But instead of the x f of x, we use a plus h f of a plus h. So this is all we're saying. If you have a point, that's the x-coordinate here is a. If I want to have a second point that's to the right of it, I can just add something to that a, right? So like let's say a is 2. If I do 2 plus 1, that would be 3, and it would be to the right, wouldn't it? If I do 2 plus a half, that would still be to the right. So whatever this a is, a plus h, as long as h is positive, should be over on the right side of it. Yes? And then what I would need to do is try and move that point towards the other one. How would I make that happen? Tell me right here, the h between those points is pretty big, isn't it? And then here, the h between those points is a little smaller. And then here, it's a little bit smaller, and then a little bit smaller. So what are you letting h do? Go to 0, right? So it's a different limit. Instead of letting x go to a like we were before, we're going to let h go to 0, but it's the same geometric idea. So we have a point, a f of a. We have a second point that is not x f of x, but a plus h f of a plus h. We connect them. We have our rise over our run. This is all from last class. But I want you to notice a couple of subtle differences here. The rise is going to be the y2 minus y1. So it's f of a plus h minus f of a. That's the top of the difference quotient. The bottom is the run, which is the x2 minus the x1. And when you actually do that, what's a plus h take away a? You're just left with h. So your run on the bottom is always h. So this is what we get. The slope of the secant line in this new formula, this new approach, instead of it being f of x minus f of a over x minus a, is f of a plus h minus f of a all over h. So that's the second of two formulas that you should know. The good thing is there's only two. And then do you remember how we came up with the equation of the tangent line, or the equation of the secant line? We put that slope right here in front of that. That was our m in that formula. Does this all look familiar? Y minus y1 equals m times x minus x1. There's the formula. That gives us our secant line, blah, blah, blah. But we want to let h go to 0. Whenever we let h go to 0, what happens? You get 0 over 0, right? So at the end of the day, it turns into this. The slope of the tangent line is that new difference quotient over h, or f of a plus h minus f of a all over h. H is going to 0 instead of x is going to a. All right, so I'm not going to go through all this. This is the same exact construction as we did before. All right? What I want to do is get to a summary. And this is where I summarize. Here they are. This is now going to be a definition, all right? The derivative of a function. Remember, this chapter is called derivatives. There are two formulas for the slope of the tangent line now. The one from last class, which you got to do on your take-home quiz, and the one from this class, which I haven't given you an example. We haven't used it yet, but let's just say that's the new formula. These are so widely used that we have special notation for them. It is called this. The derivative of the function f at the number a is either one of those. Okay? You can use either one. They're equivalent. They give you the same answer. But we use the notation f with this little, what we call prime mark, f prime of a. F prime of a are these two limits. And there I'm saying f prime of a, the derivative of f. So if someone now says to you, hey, I want you to find the derivative of this function at a, you have to go evaluate this limit or this limit. It's your choice. Understand? Geometrically, what does the derivative represent at a? Geometrically, what is it? There, come here. Here's the function, right? Right? There's the function. If I actually figure out the difference quotient, right, and take the limit, it gives me the slope of this green line, doesn't it? The slope of the tangent line. So the derivative of a function at a is equal to the slope of the tangent line on that function at a. Yes. This is a curve, right? We call it f. If someone says, hey, look, what is the derivative of this function, of this curve, at, let's say, this value x equals a right here? What is it? What's the derivative of that? It's the slope of that green tangent line. That's what it is. It'll give you a value, right? And it'll represent that slope of that tangent line. Okay, so let's... whoa, I went way too far, sorry. Where was I? There it was, right? Derivative. Okay, so what I'd like to do is another example. How about this quiz? Which one was harder? First one or the second one? First one? Anyone else? The first one was harder? Okay, so what I'm going to do here, you were asked to find the slope of the tangent line at a, right? That's what you're asked to find? Basically, I'm asking you to find the derivative of the function at a now, right? That's the new wording for today. So let's try that problem again. Find f prime of a for the function f of x equals 1 over x plus 1 squared, right? That's the problem as it was posed. No, I mean, as it's posed today, as it was posed on the quiz, it was find the slope of tangent line at a. That's what this means. So it's like a condensed notation. It's instead of saying all that, we just write that. So I have two options, don't I? I can use one of these two formulas. I can use that this is equal to the limit as x approaches a of f of x minus f of a over x minus a, which is what you all did, right? That's what you all did for your take-home. Or now I'm equipped with this new version of the formula that says this. The derivative is equal to limit, but this time what? H goes to 0 of f of a plus h minus f of a all over just h. So what I'm telling you is that you are free to use either definition of the derivative as you wish. On a test, if I say find the derivative of a function using the definition, you can choose one of these. You have that free will. Now, sometimes the algebra using one is easier than the algebra using the other. We're just going to have to see. All right? So let's see if using this one is any easier than using this one. We saw this one kind of sucked, right? Let's see if this one's easier. I'm not guaranteeing you it is, but I want you to see how it would give us a sort of a different result. Or not the same answer, but a different way we get there. So I'm going to put limit h goes 0. F of a plus h means I'm replacing this x with a plus h, right? Into that function right there, that x gets replaced with a plus h. So I'm going to write 1 over parentheses a plus h, then what? Plus 1, and then squared. Then minus f of a, right? F of a, so I'm replacing the x in here this time with just a. That's nice because that's not going to be too bad, I think. A plus 1 squared all over h. Okay, that doesn't look that much better than what we had before. How would we do this? How would you figure out what that is? Common denominator, right? That was kind of the trick that we were using. The algebra. We do get 0 over 0. I mean, you can check it yourself. Let that h go away, and this expression is exactly the same as this expression. They cancel out. You get 0. You let this h go to 0. You get 0 over 0. So, all right, so common denominator. So I'm going to multiply this top left by what? Plus 1 squared. And I have to do that on the bottom also, right? I'm just going to do it like that. So I'm doing the top and bottom here by that. Over here, what? The a plus h plus 1 squared over a plus h plus 1 squared. So this is very similar to the other approach. I don't think there's a whole lot different right now, is there? I mean, as far as we still had to get a common denominator, they still kind of suck. Keep going here. I have the a plus 1 squared on the top left. Minus, so that's this minus right here. Then this right here is just the a plus h plus 1 squared. All over what? The common denominator, right? Which is a plus 1 squared times a plus h plus 1 squared all over, everything over h. Again, if you were to look back at the work for the one you took home, this is still very similar to what we've done. Now, I'm hoping to get this h to cancel. Up here, I need to clean this up. But to clean that up means I need to expand those, right? Like I have to figure out what's a plus 1 times a plus 1, and then a plus h plus 1 times a plus h plus 1. So maybe I do those over here. A plus 1 squared. I would expect everyone in this class can do this one without too much of an issue, right? That's what this would become. The other one, though, let's just be careful with it. A plus h plus 1 squared means a plus h plus 1 times a plus h plus 1. And then you have to do like an expanding. You start here at A, distribute it to all three of these. Then you go to the H, distribute it to all three. Then you go to the 1 and distribute all three. This mouse sucks. My mouse is missing, but this one is not as accurate. So what do we have? First multiplication here, we get A squared, then plus AH, then plus H. So that's the A going through to these three. Now H through. So AH, next. H squared, next. Plus H. Now the 1 goes through. I'm out of room. So plus A plus H plus 1. First what? First A. Hold on. I believe you, but let me just catch up. A squared, AH, A. Yes, right there. And then everything else looks okay. Okay, good. Glad you caught that. That was going to cause major problems. All right, so the top left here is this, minus the top right, which is this. Remember that minus sign will be distributed through everything here. Everything. So let me rewrite the problem. Limit H goes to 0. Let's see, we have A squared plus 2A plus 1, then minus A squared minus AH. I think I have more than one AH, don't I? Minus A, minus AH, minus H squared, minus H, minus A, minus H, minus 1. Right? All over A plus 1 squared times A plus H plus 1 squared. So there's my common denominator, all of that over H. And I'm going to get some good canceling here. A squared's gone. This 2A cancels with that minus A minus A. This AH, oh no, that doesn't go away. The 1 and 1? Anything else? That's it. That's it. So I have, still on top, doesn't matter what order you put these in. How many AHs do I have? Negative 2? Negative 2 AH. Let me see. I have a negative H squared, and I have a minus 2H. All over A plus 1 squared, A plus H plus 1 squared. Ugh. All over H. Now what can I do? Factor an H out of the top, and then cancel it out. Can you? No? Okay. Equals limit. H goes to 0. So I'm going to pull an H out of the top, and then I'm going to cancel it. So I'm not going to show that canceling. That'll leave me with the negative 2A on top, minus H, what else? Minus 2, all over A plus H, no, A plus 1, squared, A plus H plus 1, squared. And we've canceled the H, haven't we? At this point, I can let H go to 0. This mouse is ridiculous. Take for granted how good that mouse I was using was. What's that? It should, yes. The derivative is unique. So when you do the limit here, you get no more limit, right? We've taken the limit, all the h's go to 0. So negative 2a minus 2 over, this is a plus 1 squared. This is also an a plus 1 squared. So it's a plus 1 to the fourth. And then we were hopefully you saw that you could factor a negative 2 out of the top and get an a plus 1 factor to cancel and leave it with negative 2 over a plus 1 cubed. All right, we're going to take a vote. What I'd like to know is whether or not you think that this way was easier than the other way or not. So yes, it was easier, or no, it wasn't, or even say no if they're about the same. Yes. Yes. Well, yeah, I replaced this with 0, and when I did, it was minus 0, so it is gone. And I replaced that with 0. This is just a plus 1 now. So I don't know if I'm answering your question. I am actually letting h be 0. That's right. It's not multiplication, so it's like it wasn't there. You think this was easier? Yeah? Okay. Yeah. Well, like I said, in some cases, this formula is going to be easier. In some cases, the other one will be easier. And sometimes they are both easy, and sometimes they both suck. So it just depends. But it's good to have it in the toolbox. Now, I prefer this one. And it's only because of where we're going. This format is used more frequently. All right? All right, well, that is pretty much it for the new notation. Oops. But let's talk a little bit more about what this derivative is, because obviously we're studying. I told you it's one of the biggest topics in the class, so it's got to have some meaning to it, right? Geometrically, we saw that it meant the slope of the tangent line, right? That's what it meant at that point, A. But not only does it represent the slope of the tangent line on a curve, it also represents the instantaneous rate of change of the function at the number A. What? Okay. So let me try and elaborate on this just a little bit. Time, distance. You get in your car, you start driving to school. You get here. It takes you a certain amount of time. Let's just say 20 minutes to get here. Let's say you live 7 miles away. Okay, 7 miles. Okay, let's say that's the case. Then if you connect these 2 points with a straight line, that doesn't look very straight, but if you connect those 2 with a straight line and find the slope of that line, what's the slope of this green line? Rise over run. 7 over 20, right? Yes? 7 over 20. You know what? Let's make this a little bit easier to comprehend. Let's just make this 20. Let's just make it 2 hours. And let's make this 70 miles. Okay? This will be much easier to kind of rationalize. Changing that to 70 and a 2. So what does the slope of this line represent? 70 divided by 2 is what? 35, right? And that would be miles per hour. Miles was the y-axis, yes? Distance, or time was the x-axis. If you take the rise, which is your hour, or miles, and you divide it by your run, which is your time, your hours, you get miles per hour. So this green slope represents your average speed, doesn't it? Your average speed through the whole trip. Took you 2 hours to go 70 miles. That's your average speed. But that's not what we're interested in a class like this. Because when you're driving, you slow down, you speed up, you slow down. You're not driving 35 miles an hour the whole time, right? So if you look at the actual blue curve and you pick some point, let's just say right here, and we call it A, and we go up to that curve, and we look at the slope of the tangent line, it's still rise over run, right? Rise being miles, run being time, hours. And so the slope of that tangent line gives you the speed at that instant in time, doesn't it? which we said to have speed, right? To have speed, you have to have some idea of a distance divided by a time. And at an instant, we said you don't go any distance, right? And there's no time, so it's like 0 over 0. But see, we've gotten around that, haven't we? We actually have an answer to this. We can talk about the speed at an instant in time by just looking at the derivative using a limit. So that it's not, I'm trying to get you to see that there's a connection. Geometrically, it's a slope of a tangent line on a curve. But if the y-axis is miles and the x-axis is time, right, hours, then it's an instantaneous speed in miles per hour. Yes? Now let me change this completely. Let me do a different graph. How about in chemistry, you have, let's say, temperature, and over here you have time. And so you start this chemical reaction, you measure the temperature of whatever it is, some liquid inside of a glass, what are those things called? Beakers, right? And then you measure the temperature at the beginning, you run this chemical reaction, and it does this, and then goes like this. Let's say it does that. Then geometrically, you look at this graph and you say, okay, it's a curve, right? And I could find the average rate of change by connecting these two together, right? The average rate of change here looks like it would be 0 though, right? Because your rise is nothing, right? Rise is nothing. That's not what we're interested in. In a chemistry experiment, we would want to know when was the temperature going up the fastest. So look at this. If I pick this point right here, the slope of the tangent line represents you tell me, the instantaneous rate of change in what? Temperature with respect to time, right? So maybe in degrees per second or degrees per hour, something like that. Now, is this where the temperature was going up the fastest? No. Where would that be? Wherever that tangent line is what? The steepest, right? The steepest you could ever find on here. So would you agree that right here, the temperature was increasing faster? Yes? And so now this curve, these slopes of these tangent lines is connecting how things are changing at instants on curves. And we want to know when it's the steepest. We want to know maybe when the temperature stopped changing, when the change was 0. And that looks like it happened right about here. The slope of the tangent line right about over here looks like it's 0, doesn't it? Then after that, it started dropping off, right? Temperature dropped down. And so these are, steep tangent lines, but those are negative, aren't they? Over here, they're positive slope. Over here, it's negative slope. Do y'all see this? Understand? And you could do this for any two quantities you want. You could let this be money, and you could let this be number of employees. So maybe you're a business where the more employees you hire, the more, like, I don't know what kind of business. You're selling stuff legally, selling stuff. And let's say, if you have one employee, you're going to have a certain number of sales, right? You have two employees, you're going to have more sales. And maybe you're able to determine that the number of employees is directly related to the number of sales, but at some point it gets too expensive to have the employees, so it kind of like plateaus out or something, right? Then what you're trying to find is, things like this would represent, that slope of that tangent line would give you the instantaneous rate of change in what? Money, dollars per employee, right? So you try and find where you're going to get the steepest. Does that make sense? I mean, we're looking at the graph. The slope tangent line is the overall picture, but the two quantities it's connecting can be anything. So in physics, you have, force, time, right? The rate of change, it's going to find the instantaneous rate of change at that point. What we're going to ask later is what's the highest point on this graph? Well, do you notice something about the highest point on that graph? What's the instantaneous rate of change there? 0, right? So guess what we're going to do? We're going to take the derivative, figure out what it is, and then set it equal to 0. And whatever that solution is corresponds to where that is. Make sense? So that's where we're headed. And so you can take any function and pretty much find where all those humps and valleys are on pretty much anything using that approach. There's more to it, all right? But because you can have a situation like this where you have a maximum point on a curve like that, but see, look at the tangent line is weird there. At the top, it's not 0. So we're going to talk about that. All right. So in the case where you have a curve that gives you the displacement of an object, distance, in miles. Sorry, you can't read that, miles. And this is time. Then the slope of the tangent line is your instantaneous velocity. So I have 1 point, 2 points. This right here, 8.3, let me move this first point over. The slope of this purple line right here is the average rate of change between these 2 points. But if I slide that second point closer, look at what happens to the slope. What happens? What's it getting closer to? 8.8. Oh, hold on. 8. I went too far. 6.7, right? 6.5, 6.3. What's it getting closer to? What does it look like it's getting closer to? 5? And then when I actually get there, it is 5. That limit does give you 5. So it doesn't, look, this would not be calculus if I was just taking 2 points on a curve and saying find the slope and line between them. That's not calculus. Calculus is you move that point on top of the other one and you're talking about something at an instant instead. But to do it, you have to have a limit, right? Okay, that's pretty much it. Do you feel like you want to see another example of that formula? I can give you another example. Yeah? Let me look at your homework because I was about to put it up here. All right, how about this one? This is a homework problem. So they give you capital, this is number 23 in the homework. This is part of your homework for tonight. But I'm going to do this one. So that's not what they ask you in the homework. They ask you to find f prime of 2, but I'm going to say, what's f prime of a? So I'm asking for the derivative of capital F, right, at the value a. So this curve, when you graph it, it's doing something. And if you went to a specific point A on the x-axis and looked up on the curve, this is going to give us that pitch of that line. So what do? What is the definition of the derivative? In this case, using capital F of A, F prime of A. The definition is limit, right? Now you get two choices here. You want x goes to A, or you want h goes to 0. Well, let's practice with h goes to 0 because we didn't do that. We've only done one of these. Then what is it going to be? Okay, capital F of A plus H minus capital F of A all over H. That's the definition. The only difference is that the name of this function is capital F instead of little f, so I'm just replacing the little f's with capital F's. But that's the definition that I'm choosing to use for this. If I can figure out what this limit is, that represents the slope of the tangent line there. So now let's replace A plus H in this formula. Oh man. Do you see how bad this can be? Okay, replace A plus H in there for X. You get 5 times A plus H on top over 1 plus A plus H quantity squared. That's F of A plus H. Minus, what's F of A? 5A over 1 plus A squared. That's not so bad. All over H. Oh man. What you're going to need? Common denominator. Get used to it. I'm going to give myself a little more room out in front here so I can squeeze that common denominator in there. So what's going to be put in here on the left side here? 1 plus A squared. Over here on the other side, on the right side, I'm putting in what? 1 plus A plus H squared, 1 plus A plus H squared. And if you ever get to a point in this class where you feel like this algebra sucks, that is what I've promised you, right, from the beginning, is that the algebra is what makes this course the challenge. You know, the formula is the formula. There's nothing to that. It's the algebra now that's required. So let's try and clean this up. This one, how do you want to do this one? Multiply that all together? How would you do this? You want to distribute the 5 through here first? You could do that, and then after that, put these all together. It's your call. I don't mind that. Let me do that. So if I multiply that through, I just put the 5 through. I haven't done anything else. I'm going to put this over here too. Minus my 5A has to be multiplied times 1 plus. Is it okay right now if I just multiply this out mentally, A plus H times A plus H, and put A squared plus 2AH plus H squared right there? That's okay. Now the reason I did that is because I realized that after I multiply that out, I'm just going to come through with the 5A through the whole thing. And so it's not going to be too bad. Everything here is going to be over my what? Common denominator, which is 1 plus A squared times 1 plus the quantity A plus H squared, the whole thing over H. Man, I can't believe it's already 140. Yeah, bless you. All right, here we go. Let's start to put that top together to see how fast we can do this. All right, 1 times 5A, right? 5A. The next one, 1 times 5H is 5H. Now the inside one's A squared times 5A is 5A cubed. A squared plus 5AH is 5A squared H. So that's these two together right here. Then I'm going to distribute 5A through here. Actually, let's distribute negative 5A through. So what do you get? Negative 5A, then negative 5A cubed, and then minus 10A squared H, and then minus 5AH H squared. All over the common What do y'all think? What are y'all feeling right now? I mean, how? What's that? Which? Oh, the rules? Oh, the other formula. Might have been easier in this one. Might have. Did you try it the other way? No? Yeah, it would probably be a little bit nicer. But, you know, at the end of the day, it's just algebra, right? Okay, do we get good cancellation? 5a cubed, 5a. Is that it? These two can go together, right? This one and this one are like terms. So those will turn into a negative 5a squared h, right? Those two together. But other than that, nothing else goes away. But everything I have still has an h in it, which is what I'm really hoping for, right? So let me see if I can get this next line. Limit h goes to 0, 5h minus 5a squared h minus 5ah squared all over my common denominator. Ugh. Have I shared with you my recycle theory? Did I share that in a pre-cal class? No? If you're ever feeling like, man, this is a lot to write, I'm like going writing on all this paper, you know, using all the paper, huh? No, my idea on recycling, like if you ever feel like you're having, you know, like we're using a lot of paper in here, like I'm wasting paper, I'm killing trees, you know, like don't worry about it, you know. The sun is the ultimate recycler, right? The sun will expand at some point, just recycle the whole planet. It's going to be beautiful. So you don't have to worry about a piece of paper and a couple of trees. It's all going to be taken care of. All right? Don't worry about paper, man. Do not worry about paper. What? Yeah, I know. So who cares, right? Well, you're delaying the inevitable. You're delaying the inevitable, right? Okay, I totally agree. So what we have to do is we have to find value on physical sciences like chemistry and physics and astronomy, and we need to value the people that are interested in that and put money into that instead of paying some guy $50 million to go play basketball or baseball. The value where the money is, there's no research to get us off this planet to the point we could save ourselves, right? That's right. That's right. But you're going to face the cruel reality of those sciences is that the money's not there. So you have to change the perspective of the people. It's hard to do, especially in this society. What's that? Yeah, well, where are you going to find? You got to find people who believe in something like that. That the research is worth the payoff in the end. If not, then who cares to recycle? If we don't care if we're going to turn on the sports and that's where we'll put all the money in advertising, that's where all the value is, then paper doesn't matter. Should I just shut up? I should just shut up and just continue. Okay, what happens here? H, you can pull a 5 too, but I'm just going to pull the H. It's done, right? The H is gone on the top. One H from each term. Oh, h is gone. All right, now at this point, we let h go to 0. So when we let h go to 0, this whole term goes away, right? Because this time it's not being added, it's being multiplied. So that whole thing goes away. This h goes away to 0. So we're left with on top 5 minus 5a squared over 1 plus a squared. How many of them? Because this one right here, this is a squared, isn't it? So it's 1 plus a squared. So we have 1 plus a squared, 1 plus a squared, which is 1 plus a squared squared, because it's being multiplied. Is that okay? You can take a 5 out, but I don't think we're going to get canceling that we want there. Then one of them would still stay negative, though, right? Like if I pull, let's say I pull a 5 out, then I'm left with 1 minus a squared, which won't cancel with the 1 plus a squared. But it's good to see that it maybe could have happened. All right, that's it. There. So what's the slope of the what is the slope of the tangent line of this function at 2? So what's f prime of 2? That would mean plug 2 into that. So what would you get? 2 squared, right? 4. So 1 minus 4, negative 3 times 5. So negative 15 over, and then here we're plugging in 2 squared plus 1, 5, 25. Reduce that, negative 3/5. So if I graph this, and I go and plug in, go into the x value 2 and go look at this, I should have a slope of the tangent line should be negative, right? Which means that this graph is probably coming down when you get to that point on the graph. Questions? The other what? Right here? That was because when you simplify this, this just becomes 1 plus a squared. But then here's a 1 plus a squared, so you multiply them together, it's 1 plus a squared, all of it squared. This is 1 plus a squared right there. And then you have this one next to it. And so 1 plus a squared times 1 plus a squared is 1 plus a squared, quantity squared. Yes? I let h go to 0, right? So this becomes nothing, and then this one became nothing. So I think right now, I'll go out on a limb here, and I'm going to see if we did it correctly. So I'm going to put in the function. It was 5x over 1 plus x squared. We're going to take a look at it. There's the graph. And if I go to the value 2 and go up and look at the tangent line, the slope of it should be negative 3/5. Well, it looks like it would be negative, right? So at least I feel good about that. Okay, so I can use this thing to do it. By the way, I went back and looked at my lecture. I was like, what an idiot. All I have to do is just type in 2 and then just put mark point, and then I should be able to tangent from there. Why did that happen? There we go. Yeah, see, it keeps that, well, secant. I'm going to do it again. There, see how it marked it and kept it there? That's what I meant to do last class. But I'm supposed to go to the value 2, right? Okay, there it is, right there. Now I want you to look at this right here. You see what the computer's already done? I'm at the point 2. I've asked for the tangent line there, and it's given me the slope. What is it? Negative 0.6. What's negative 3/5? Negative 0.6, right? So that matches what we got with our math. Now, while we're here, I'm curious. What is the highest point on this graph? Where does it happen? It looks like 1. Well, would you agree that when we are at the top, the slope of the tangent line up there is what? 0, right? The slope is actually 0. So couldn't we just go back to this right here? Wasn't this the slope of the tangent line? Couldn't I just set that equal to 0? Say, when is this 0? For what a is it 0? And think about this. When can a fraction be 0? Only when the top is 0. Right? A fraction can only be 0 if the top is 0. We'll talk more about that, so don't worry. It's not like I just gave that to you and you'll have to remember it for the rest of the semester. But that's true. A fraction can only be 0 if the top is 0. So set this equal to 0. You take 1 minus a squared, factored it to be 1 plus a, 1 minus a, difference of squares, right? What about the 5? Why didn't I include the 5? 5 can't be 0, so I just throw it out, right? Divide both sides by 5 and it's gone. So what does this look like my two solutions would be? 1 and negative 1. Well, at 1, looks like we have a flat horizontal tangent line, right? And what else? At negative 1? Well, what do you know? It's there too, right? So we're able to identify where these are going to happen, but we needed to have the derivative to do that. All right. I'd like to take a poll because I'm not sure if the look on your face is one of, it's a Monday. Whoa, it's like it feels like a Monday. What the hell? So the question was, do you hate this? And I guess everyone's voting. I haven't said what. So no, seriously, are y'all okay? I mean, with what I've done so far? Yes. Any questions on the algebra? I'm sorry? The what? Are you saying, I set this equal to 0, right? Which whenever you set a fraction to 0, all you have to do is look at the numerator. So if I take this numerator and I set it equal to 0, I should have had this. 5, 1 minus a squared equals 0. Divide both sides by 5 because you don't need it. That gives you this. Then I just did difference of squares, and then I just set each one equal to 0. I got two answers, 1 and negative 1. So what we're saying is, if a is 1 or a is negative 1, you're going to get a slope of a tangent line of 0, which might correspond to the top or the bottom of a graph. Might. It doesn't always. All right. Let me put the homework up here. I gave you some homework last time, right? Just a few problems. So I think what you should do is you should look at page 80 now. I think you should be working through problem 1, part A, and B only. What did I give you last time? 3, 4, 5, 6. So I'll just write them back up here in case you didn't write them down last time. 3 through 6. But then in addition to that, you should look at 7, 9, 11, 13. I guess I could have said 7 through 13 odd. 21. I have these circled. I just want to make sure it's what I want now. 23 we just did, so you don't have to worry about that. 25, 29. And that should be good. Now look, I'll warn you, a problem like number 11, let me just read this to you. A ball is thrown into the air with a velocity of 40 feet per second. Its height in feet after t seconds is given by this equation, y equals 40t minus t squared. Find the velocity when t is 2. I didn't show you anything like that. That's right. The equation is given to you. That's your function. It's saying find the velocity at t equals 2. That means go find the derivative at t equals 2, right? Or a equals 2. So you have to be able to extend on what I've said here and apply it to the problem. Hopefully that'll go okay. If it doesn't, you just ask me questions next class. Excuse me? That's right. That one, it didn't matter because they said it's 40 feet per second. As soon as they gave you the equation, you didn't need anything else as far as that 40 feet per second. Yeah. So see how you do with that. I want to see if you can translate the word problem into the math. All right, so now, just when you thought everything was okay, we just said that the derivative at a point A, right, is this limit. And I gave you two definitions. Remember that A was any number I picked, right? A was just some arbitrary letter I came up with. Yes? I could have called it C. Could have called it Q, M. What about if I just call it X? Then this formula just changes to be what? F of x plus h minus f of x over h. Same limit, h goes to 0. This would still represent the same thing. It would represent the slope of the tangent line to the curve, but instead of at the point A, f of a, it would be at the point x, f of x. So I'm just changing the letter, that's all. So our answer should have an x in it. Like the problem I did here, our answer, right? Our answer had what? A, right? Our answer had A. If we do this whole problem, we come back and replace all these A's with X's, then our answer should have X's in them. Yes? Now, why would we want to do that and complicate things? Well, because what we're doing is, I'll show it graphic, I'll show it with a visual. We're starting with a function f, right? And then we're finding its derivative. And I could call that this, f prime of x, yes? So you start off with this function, and you do this thing called taking the derivative of it, and it spits out a new, what? A new function. Do you see that? Like I start out, if this started out, what was the problem we had before? It was 5x over 1 plus x squared, right? That was it? We found the derivative. When we did that, it gave us this stuff with a's, right? But let's replace those a's with x's now. And what would we have? It was 5, then was it 1 minus a squared? So x squared over 1 plus x squared squared. Yes? That was our derivative with the a's replaced with x's. Y'all follow me? Y'all look completely zoned out today. This is the reason why I want to make sure you're still here and paying attention is because this is the first time you've ever seen this probably in your life. This is called a functional operator. It's nothing that we've ever looked at before. So think of it this way. When you're taught at some point in your life that 3, if you take that number and you do something to it like double it, then it spits out 6, right? This right here is called a function. It takes in a number, it spits out a number, doesn't it? Yes. You can even look at the operation of like addition. If you take 3 and you take the number 2 and you add them together, right? You get 5. This is an operation that takes 2 numbers in, right, and spits out a new number by adding them together. We have never had something like this before, where we take a function and we spit out a new function called its derivative. Now, we've had functions where you've done like f plus g, f minus g, right? F times g, where you take 2 functions, you add them, subtract them, multiply them, divide them. You've even had composition, right? F of g of x. But you've never had an operation that takes a function, does something to it, spits out a brand new function that's somehow connected to this. And so we call these functional operators. It eats functions and spits out functions, as opposed to this where it eats numbers and spits out numbers. See the difference? Functions like numbers to numbers. Functional operators like functions to functions. So this operation, going from a function to its derivative, this process is called differentiation. And what I'd like to look at now is how we can connect the graph of a function to its derivative. There is a visual connection. So here is the graph of a function. This is f of x, okay? Tell me right now, what is the derivative of this function at 0? What's the derivative of this function at 0? 0. Do you all agree with that? Let me see if this works. The derivative of this function at 0 is 0, because if I come here to 0, draw a tangent line, the derivative is the slope of that. What's the slope of that line? 0, right? So the derivative of that function at 0 is 0. So imagine now that I come over here and I tell you on a different set of axes to graph, don't graph f here, I want you to graph its derivative here. What can you tell me about the value of the derivative at 0? What is it? We just said 0. That means at 0, it spits out 0. So this is the graph of the derivative of that function so far. Let me get another value. What do you think the slope of the tangent line is? Not here, but maybe, say about here. What do you think the slope of the tangent line is there? You're going to have to guesstimate. Is it positive or negative? Tell me that. It's positive, right? Maybe like around 1. I don't know. Maybe 1. Can we say 1? It doesn't look like 1 because this ratio is off. The scales are off. But would you agree it's a positive slope? Yes? So if I come over here to graph its derivative, that means if I go to the negative side over here to about whatever this value is, it should spit out a positive number, something like that. Is that okay? It's a positive number? Now let me move this point closer to 0. So right there. The slope of the tangent line here is still positive, isn't it? But what? Not as positive as the one before? So where would it be over here? Above the x-axis, but not as high as that point. So somewhere like right in here. You following this? Eventually, as I get closer, right, it's still positive, right, but smaller. So it looks like this would somehow maybe connect together somehow, right? Maybe? That seem reasonable? That seem reasonable to you? Let's go to the other side. Let's see what's happening over here. Once I get to 0, tell me about the slope of the tangent line there. It's negative, right? How about here? Negative, but even more negative, right? So our graph should look something like this. When we got a little bit to the right of 0, we had a negative value. We went a little further to the right, it's even more negative, right? But what happens when I get out to that bottom point out here? So let's look at what's happening. You're telling me it's negative, right? Negative, negative, still negative? Okay, still negative? What's happening to it though? It's still negative, but it's flattening out, which means it's not as negative as it was before, right? And eventually, where does it have to go to? 0. Now, I could have put the slope of tangent line, but I didn't want to just give it away. I wanted you to make sure you were seeing it in there, right? The slope of this line is negative. but as I move, it's flattening out. So when I draw this picture of the derivative, it's going to be negative, but then it's going to have to go back and eventually go back to where? 0, right? And then what happens when I go past that point? It's going to start being positive again, which means over here on my graph, it's going to start being positive. I hope you can make that connection. Now, let me just slap the derivative right on top. Superimpose the derivative on that graph. There it is. And let me bring the screen back down. Because what we want to be able to do is have a function and then have to be able to slap the derivative right on top of it, just so you can see it. Now, I'm also going to bring in the value here. So let me go back to here. See at this value right here? The slope of this tangent line is exactly negative 2.6. So on the green one, which is the derivative, what I do is I say at that point on the derivative, I put a point at negative 2.76. And then I keep moving along. Let's see, 2.76, that's pretty steep. Negative 3.48, and then it's starting to flatten out again. Now notice this, it turned, right? Does that mean that the derivative is positive right here? No, look, the derivative is still negative, right? But it's trying to make its way back to 0 to flatten out on the original function. Let's take a poll. People always have trouble with this, so poll is open, yay or nay on this. This is always, as long as I've been teaching this or trying to help people see this, it's always been a light bulb that either just never goes on or goes on and everyone's happy, or the light bulb burns out. And then, so let's take a look at what you all said here. Oh wow, okay, so that's what I expected. All right, so let's do something a little more basic, okay? Sometimes we push as far as we can. We see how that works, and if it doesn't work, we try something a little more easy to relate to. So I'm going to draw a graph. This graph is going to be F. Here it is. F is going to be in black. I'll label it. It's just going to do this. Okay, this is the graph of F. I would like for you to tell me about its, oh man, I shouldn't have done that. Well, you know what, let's see how you handle this. This is still basic enough. So tell me about the slope of the tangent line. Let's just pick an x value. How about at -1? Tell me about the slope of the tangent line here. +1, right? How about at -2? What's the slope of the tangent line here? +1, right? What's the slope of the tangent line at -3? +1 again. And over here at -4, what's the slope of tangent line? +1. Do you agree that if you're anywhere on this side of 0, right, 0's here. If you're anywhere on this side of 0, the slope of the tangent line is 1. Yes? So the derivative, when I draw it, needs to be a constant 1 function to the left of 0. So here comes the derivative. I'm going to draw this one in green. We said at -1, it's 1. We said at -2, it's 1. We said at -3, it's 1. We said at -4, it's 1. Do you see that the height of this function corresponds to the slope of the line, tangent line on the curve at that point? So whatever the slope is here, plot it, 1. Slope here, plot it, 1. Slope here, plot it, 1. And if you connect everything in between, you get a flat line like this. What about on the other side? So at 1, What's the slope of the tangent line at 1? Negative 1. What's the slope of the tangent line at 2? Negative 2. What's the slope of the tangent line at 3? Negative 1. It's always negative 1, right? If I'm to the right of 0. So where am I going to draw this? Constant function? Where? Negative 1. So down here, negative 1, negative 1, negative 1, negative 1, and it continues that out the right side forever. Now, the interesting thing, and the reason I said, oh man, is what's happening at 0. We have a corner. We haven't talked about it yet, but derivatives do not exist at corners. So what happens is on your derivative function, you're going to have open circles here, meaning that your derivative is not defined at 0. So your derivative has a jump in it, doesn't it? Your original function is continuous. You can draw without picking up your pencil, but your derivative is not continuous. It has a jump. Okay, let's take a poll on just whether or not you see the connection between that function and its derivative now. It's okay to not. I just need to know. All right. Do another. Okay, I'm going to draw a function, and let's try and draw its derivative, all right? So I'll draw the function in black here. That's supposed to be somewhat symmetric. It was supposed to look the same way in both directions. That's f. Okay. When I'm starting to look at a function, try and draw its derivative, I always try and find a point that I know something about. Like in the previous problem, I said, look, this is a straight line. All straight lines have the same slope, right? So I just picked some point over here, say, hey, at negative 1, the slope's 1. Negative 2, the slope's 1. I want you to do the same thing here. Do you know the slope of the tangent line for sure at any point here? It looks like at 0, right? At 0, here's the point on the curve. What's the slope of the tangent line there? It's 0, right? Slope is that tangent line. That slope is 0 because it's a horizontal line. So when I draw its derivative, when I draw the derivative at that point, where do I need to put the dot? At 0, right? So on the x-axis, I'm at 0. On the y-axis, I'm at 0 because the derivative is 0. So I'll do it in green here. Now, let's move to the right. Tell me about the slope of the tangent line right here. Just tell me about it. Describe it to me. It's negative. Is it big negative or small negative? Small negative. Okay, describe the slope of tangent line here. Big negative, bigger, right? Here? Bigger. It's hard to tell, right? Might be bigger, might be smaller. But tell me about the trend of what's happening to the slope of tangent line as I move out here. It's going to get smaller, but it's still what? Negative. Yes? So let's recap that. As I move to the right, the slope of tangent line was a little negative number, and then it got to be a pretty big negative number, and then it went back to being a very, very small negative number. But it stayed negative, didn't it? So how do I draw that? I need to draw to the right a curve that starts out little negative, gets kind of big negative, but then goes back to little negative, and always stays little negative. Okay. Sounds like I'm talking preschool up here, right? It's a big negative and a little negative. I mean, this is calculus. It's weird. All right. Yes or no? You get the big negative, little negative thing I'm talking about here or not? All right. So bonus. Who wants bonus? You come up here and draw the derivative. I don't know, something. No volunteer. You can just go up there with the ruler and just show me what you think it is. Anyone? No? Go for it. Just pick up that ruler right there and just kind of trace out what you think it is. Doesn't have to be perfect. Okay. Okay. Good. That's fine. And then what? Keep going to your right. What's it going to do? So as you keep moving this way, do you agree the implication is that that's an asymptote? Yes. So it's gonna stay. Do you agree it's gonna stay like pitched down a little bit? It's gonna keep decreasing. So it's gonna stay negative, small negative. Hold on. You were good, but you just hadn't finished it off. You said that it started out little negative, but then it got a little bigger. But then because it flattened out, it's gonna have to come back here. And then you were kind of like, well, what happens now? But it has to stay. These tangent lines, each one of these, as I move out, still is pitched down just a little bit, right? Smaller and smaller as we go. So can you show me that on there? Start over. Start at the beginning. Little negative to bigger negative, then back to little negative, right? You're going to little negative, getting closer to little negative, even smaller little negative, smaller negative, and you just keep doing that. It's actually approaching flat, right? But it never gets there. What's flat? Flat's zero. So you're approaching zero without ever getting there. So it looks like this. Good job. We'll work out your bonus some other time. That's what it looks like. Wow, that's kind of bad. I don't like that. So the slope of the tangent line here is 0, but as I move to the right, it's little negative. It gets bigger negative, and then it starts to go the other way. It's still negative, but not quite as big, and then it starts flattening out so that it's still a negative number, but it's just smaller and smaller and smaller and smaller and smaller and smaller and smaller. How about this side? Kind of the same story, but when I'm moving this way over here, tell me about the slope of the tangent line here. Small positive number. A little bit further, positive, a little bit bigger though, right? Move over here, a little bigger positive, and then still positive, but now getting smaller and smaller and smaller and smaller. So as I move from right to left this way, it's going to be small positive, getting bigger and bigger, and then coming back to small positive. So it's going to look like this. All right, let's take a vote. Okay. Okay, you ready? You might appreciate this. How's it 80-15? How's that possible? I know. Someone hit C. Is that I'm neutral? I don't care. Sun's gonna swallow us up anyway. All right, let me give another one. I don't care about paper or calculus. You might like this. You may not. Hey, hold on. I haven't even finished. This is not drawn to scale, but it is a scale nonetheless. All right. This has potential to give you goosebumps if you like this sort of stuff. If math ever gives you goosebumps, this might do it. It may not. I'm not sure. Depends on you. All right. Damn. Show me what the derivative of this looks like. So let's draw its derivative. Does anyone recognize that curve? That's sine. Okay, let's talk about its derivative. Tell me where you know for sure something. Where is the derivative 0? Where is it happening? Right up here, right? That corresponds to this value, which is actually pi over 2. This is pi. This is 3 pi over 2, right? So we all are comfortable with the idea that at this point, pi over 2, the slope of the tangent line there is 0. Therefore, the derivative, when I draw it, should be 0 there. So here comes the derivative. I'll do it in blue. There it is. Now, where else can you tell me the derivative is 0? At 3 pi over 2, which is here. Yeah? All right. Now let's start moving here. From this point, tell me about the derivative as I come this way. Starts out what? Small positive. It's getting what? Steeper, so bigger positive until I get down to here, and it looks pretty steep, right? Like maybe it's the steepest out of all of that. Big positive. So let's move the other way. Big positive until you get to small positive to 0, right? So maybe it looks like this. Big positive until it gets to 0 like that. Maybe. Now tell me about what's happening over here. It's going to be small negative until you get to what? Big negative, big negative. Now tell me what's happening here. Come on. What's happening? Am I still negative or not? Slope of tangent line. Still negative, but what's happening? It's heading back to 0. So when I move from here to here, I need to go negative, get real big negative, and then go back to 0, which is going to be like this. And then, once I get past here, tell me about it. Small positive until I get to big positive. And so it's going to look like this. And that is cosine. So it turns out that the derivative of the sine function is the cosine function, which we'd have to prove. But that geometrically shows that it might be connected. Now, the next question would be, does it work the other way around? Is the derivative of cosine sine? Do you think? What do you think? Oops. Shall we try it or not? Let's just see. I think it'll work pretty quickly. I mean, come on. We have to step back and appreciate this. I said it was goosebump worthy. If you have a spring, something that has, some sort of oscillating object, right? And it's moving in a pattern of a sine curve. What we've just said is that if you want to know the speed of the object at a point in time, all you need to be able to do is evaluate a cosine function. That's it. That's all you need to be able to do. So if I say, what is the speed of this object at pi over 2? You would say, oh wait, no, the green one was, sorry. Yeah, what's the speed of the object at pi over 2? 0, right? You've got a thing that's moving up and then down. At pi over 2, it was at the peak. The speed at the peak is 0. And then it starts coming down. That's good stuff. I remember taking a physics class that was calculus based, and I hadn't taken the calculus, and they had a sine curve, and they're like, and the velocity of the sine curve is the cosine curve, and I'm like, what the hell just happened? Like, how does sine become cosine? I was so confused. It was because they were taking derivative, and I'd never seen a derivative, so it didn't make sense. But I was kind of getting the carriage in front of the horse back then. So let's try the cosine. See if it works the same way. So cosine looks like this. And tell me one place you know for sure about its derivative. At pi, right? At pi, the derivative should be 0. Okay. Oh, wait, there's other places. Sorry, this drawing sucked. It goes like this, like that. They come up and they flatten out there, right? Because this does continue like this the other way. So where else is the derivative going to be 0? At 0. And then where else? At 2 pi. Well, that's looking pretty promising, isn't it? Because my sine curve goes like this. However, let's move to the right here. What happens? Move to the right, my derivative should be what? Negative small. And then it gets bigger negative, bigger negative, bigger negative, and then back to 0. Which means it's got to look like this. Terrible again. Not happy with that. And then once it gets past here, what's the derivative? Small positive, small positive, small positive. Then it kind of maxes out, and then it starts getting smaller and smaller positive. So it's going to look like this. It kind of maxes out and then comes back to small positive. So is that the sine curve? It's flipped. It's negative sine. So it turns out that the derivative of sine, remember this one right here, the original function f was the green one. F was sine x. And we figured out that just by looking, the derivative looks like the cosine function. Here, we did it the other way around. We graphed f to be the cosine function, and it looks like the derivative of it is negative sine. That's what it's going to turn out to be, all right? The derivative of sine x is cosine x. The derivative of cosine x is negative sine x. We'll have to show it algebraically at some point. Like, we'll have to actually do the limit and do all that stuff. But that's just to kind of tie it in a little bit visually. So let's just take an overall. Do you feel a little bit better, yes or no, about connecting the graph of a function and its derivative? Like, I give you a graph, you draw its derivative. Doesn't have to be perfect. You understand that? It doesn't have to like be exact. It's just to get a behavior. Okay, good. Well, I'm glad we've moved pretty far from 44 to whatever it was. All right, what's more here? So I could do this. Yeah, maybe you can help me with this. There's a graph of f. What does its derivative look like? Straight line, 3. Because the slope of that graph is 3. Okay, here's another x squared. That, you're way ahead. What does the graph of it look like? So where is the derivative going to be 0? 0. Tell me about what's going to happen over here. Small positive and then gets bigger and bigger positive. Over here it's going to be small negative, but it's going to get bigger, bigger negative, isn't it? It's going to look like this. Do you agree that at 0, it's 0? To the right, small positive, but they're getting bigger positives. Over here to the left, small negatives, but it's getting bigger negatives. X cubed. Y'all are all doing power rule that we haven't even talked about, so I can't say yes. The derivative of that is 3x squared, but we haven't even said why. So if you've seen that, you've seen it. But we're trying to see the visual here, the visual of this. So what's happening at 0? Does it look like a flat tangent line there? Yeah. To the right, what do we have? Small positive getting bigger and bigger. What about to the left? Small positive. See, these are still positives, aren't they? Derivative. So we have to the left, small positive getting bigger. To the right, small positive getting bigger. It's going to be a parabola. 3x squared. That's what it is, right? 1 over x. This one's tricky. What's the slope of the tangent line right there at my arrow? What does it look like? What's your best guess for that? Negative, right? Let's say -1. Does that seem fair? -1? Then if I go this way, what's it going to be? Whoa! Super steep negative, right? Big negative number. What if I go this way? Small negative number. So what's that side over there going to look like when I draw this? We said it was going to be -1 to the left, huge negative numbers to the right, small negative numbers. Is this what you were thinking? -1 to the left, big negative numbers to the right, small negative numbers. Is that what you were thinking? So this is a question you ask yourself. Square root of x. We have an issue. It doesn't seem to want to take the issue away. We have an infinite derivative, or infinite slope. See what's happening here, it's hard to tell here, but your slope of your tangent line, see this is positive, right? And as I go out, it's positive but getting what? Smaller, right? But if I come this way, what's happening? It's getting steeper and steeper and steeper, and actually it turns vertical as you try and get to 0. And so it gets super steep positive, which is why this is getting super big and becoming asymptotic. And then sine, we just did this. Sine and cosine. All right, just some notation. I know we're out of here in a few minutes, but this is just notation. The derivative is used so much that we have different ways of telling people we want you to take a derivative. So we already saw the f prime of x. If someone gives you a curve, y equals f of x, if they just write y prime, they mean go find the derivative. If they write dy dx, they mean the derivative. That comes from rise over run. You've probably seen this before. Delta y, delta x, right? That's what we talked about earlier, like last class. Change in y over change in x. But if you take the limit, right, once you apply the limit and you let that thing become infinitesimally small, you're letting that one point drop onto the other one, we don't use delta anymore. We use d. It's called the differential, dy dx. The differential of y over the differential of x. That represents the derivative. You may also see someone write df dx. Not used very often, okay? These first three are used all the time. This one, you'll see, used pretty frequently. They just write d dx of the function. So that's telling you take the derivative of the function. Capital D subscript x, these are used in Cal 3. So they're not used much now, but later on you'll see more notation like that in Cal 3 because you have more than one variable in Cal 3, so you have to be very specific as to what variable you're differentiating with respect to. Okay, the notation, this one right here, dy dx, is called Leibniz notation. It's named after this guy who came up. He's a co-founder of calculus. So two people developed calculus, Newton and Leibniz. Newton used his own notation. Leibniz used his own. This one is the Leibniz notation. Yeah. I know you want to go, but I still have you for a minute. This is all just definitions, why we can just run through it. A function is said to be differentiable at A if the derivative exists. The derivative is a limit, right? The derivative is a limit? Didn't we have limits that didn't exist? Okay. If the limit exists, we say the function is differentiable. If it's differentiable at every point inside of an interval, then we say it's differentiable on an open interval. So every point in there. This is a huge theorem that we won't get into too much. But if a function is differentiable at a point, then it must be continuous at a point. So you can't be differentiable but then have a jump. Remember the different discontinuities? Jump, infinite, and removable. So if you're differentiable at a point, you cannot have a jump, you cannot have an infinite discontinuity, and you cannot have a hole. So when do functions fail to be differentiable? When can you not get a derivative? When is it not possible? There's three different things. A corner, or what we call a cusp, a jump in the graph, so just like with continuity, or a vertical tangent line. So look at this corner right here. I'm showing the derivative. As I move, what's the slope of the tangent line here? It's like 1, right? And then what happens? All of a sudden, instantaneously, I go from 1 to what? -1. And that abrupt change makes it not differentiable there. So this is what we call a corner. This is a jump. So from one side, the slope of the tangent line is positive, but the other side, it's negative. Anytime you have a jump in the graph, you can't be differentiable. Vertical tangent. Why is the derivative not possible at a vertical tangent line? Or at something like this. So look at the value of my derivative. What's happening to it here? It's going to get big positive. Whoa, big positive. And as I move in closer and closer, it becomes infinite, doesn't it? Whoa, it's not working. There it goes. So look at my tangent line there. 1, the slope is 1, then it's 2, then it's 3, and then it's really wanting to take off, isn't it? And problem is we cannot define a vertical line, right? Horizontal is fine. Slope is 0. Vertical, not possible. So those are the three cases. All right. I think I gave you enough homework to be satisfied with, but I know some of you are never satisfied. So I will put some stuff down here. I know y'all really want to go. Y'all are making that very clear. But I'm going to put problem page 92. You should all do number 3. And you should all do, well, 3 through 11. Number 3 is match. They give you an F. They give you a bunch of functions, and they give you a bunch of derivatives, and you're supposed to match the function to its derivative. And then 4 through 11, they give you a function that asks you to draw the derivative yourself. I'll see all of you next class. Have a good day.